Welcome to True Projects. In this video, we will explain about the project, which is an improved lightweight YOLOv5 algorithm for detecting strawberry disease. Introduction of the project. The cultivation of strawberries has seen a significant rise in both nutritional and economic value due to the increased market demand. However, the expansion of strawberry cultivation faces a substantial challenge in the form of diseases caused by bacteria, fungi, and pathogens, which can adversely impact yield and the quality. Traditional methods of plant disease identification, relying on manual recognition and expert systems, have limitations in the terms of efficiency and accuracy, hindering real time crop monitoring. Early detection of diseases is crucial for effective prevention, but it is often challenging to identify them promptly during the initial stages of infection. Traditional image recognition techniques have shown good results but come with the limitations such as complex pre processing and subjectivity. With the advancements in deep learning methods and computer hardware, deep learning based target detection algorithms have gained prominence for their speed, precision, generalization ability, and robustness in agricultural research. The application of deep learning based detection methods has significantly contributed to the reducing of cost of manual diagnosis of plant diseases. These methods assist agricultural producers in accurately and quickly identifying diseases, minimizing pesticide use, and implementing correct measures to curb diseases spread. In response to the rapid spread of strawberry diseases and the limitations of current deep learning models, this project introduces an improved lightweight YOLOv5 model for strawberry disease detection. The proposed model incorporates innovative features such as ghost corn for model compression, involution of adaptive weight assignment. The aim is to enhance the automatic monitoring capability of strawberry diseases in greenhouses, providing valuable guidance for diseases control in more efficient and resource friendly manner. Objective of the project. The primary objective is to build and train multiple YOLO models including YOLO V5N, YOLO V5S, YOLO V7 Tiny, YOLO V5 GhostNet, YOLO V8N, YOLO V8S. Each model is examined for its suitability in detecting strawberry diseases from remote aerial satellite images. The comparison aims to identify the most effective model for this specific task. The aim is to introduce the Ghost Conv module into the YOLO V5 network to optimize model efficiency by reducing parameter numbers and floating point operations during feature extraction, ensuring a more resource friendly approach. The goal is to compare various YOLO models for detecting strawberry diseases in remote aerial satellite images based on metrics including mean average precision, which is MAP, precision, recall. The goal is to identify the most effective model that achieves a balanced performance for accurate disease detection with optimal efficiency, considering real time applications and deployment feasibility. The project aims to provide tangible benefits to various stakeholders in the strawberry cultivation ecosystem, including farmers, agricultural researchers, and industry professionals, by delivering an improved lightweight YOLO V5 model for strawberry disease detection. The project seeks to empower these stakeholders with a more efficient and accurate tool for early disease identification, enabling timely interventions and optimized disease control strategies. The overarching goal is to enhance crop yield, quality, and economic returns for strawberry cultivators while minimizing the environmental impact through reducing pesticide use. To implement this project, we need software and hardware requirements. Software requirements are application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. And the hardware requirements which are needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement the project, we have designed various steps in the flow of work. The first step is importing the packages. In this step, the necessary libraries and packages are imported into the project environment. We have imported OpenCV for image processing, NumPy for numerical operations, Torch and Keras for deep learning, Pandas for data manipulation, Seaborn and Matplotlib for visualization, Flask for web development. The next step is exploring the dataset. This step involves reading the images from the dataset, and additionally, the loaded images are plotted to visualize and understand the data. The next step is image processing. In this step, Images are transformed into a blob object, which is a binary large object for further processing. The classes of the objects to be detected in the images are defined. The bounding box coordinates for detected objects are declared. Image data is converted into a NumPy array for compatibility with the deep learning frameworks. The next step is loading the pre-trained model. In this step, the architecture and the layers of a pre-trained deep learning model are loaded into the program. The output layers of the model are identified for extracting the predictions. Coming to image processing, in this step, image data is linked with corresponding annotation files, providing information about the objects in the images. And we have converted BGR to RGB, which is blue, green, red, to RGB, which is red, green, blue. Color channels in the images are adjusted to fit the RGB format. A mask is generated to highlight regions of interest in the image. Images are resized to match the input size expected by the pre-trained model. The next step is data augmentation. Here, images undergo random transformations to introduce variety into training data. Images are rotated to diversify the dataset, and additional transformations such as scaling and flipping are applied to augment the dataset. The next step is building the model. In this step, models are constructed, which are deep learning models are constructed. It involves defining the architecture, layers, and parameters of the deep learning models for object detection. Training the model. The model is trained using the augmented dataset, adjusting its parameters to learn and recognize patterns in the images. The training process involves optimizing the model to improve its ability to detect and classify objects. Flask framework with SQLite for sign up and sign in. Flask, a web framework for Python, is used along with SQLite for user authentication. This step involves setting up a web application to handle user sign up and sign in functionalities with user data stored in an SQLite database. The next step is user gives input as an image. User interact with the system by providing an input image for object detection. The next step is the given input is pre-processed with the trained model is used for detection. The input image is pre-processed to match the requirements of the trained model, and the model is then used to detect objects within the image. The next step is each object is segmented and bounding boxes are drawn. Detected objects are segmented from the image and bounding boxes are drawn around them to visually represent the locations of the identified objects. The last step is final outcome is displayed. The processed image with drawn bounding boxes is presented as the final outcome, showing the results of the object detection process. Now we will know what are the algorithms used in the project. The first algorithm is YOLOv5n, which is You Only Look Once version 5 nano. First, we will know what is YOLO. YOLO is an object detection algorithm that divides an image into a grid and predicts bounding boxes and class probabilities for each grid cell. YOLO processes the entire image in one forward pass, making it efficient for real-time object detection. YOLO is favored for its speed and efficiency, providing accurate object detection with a single pass through the neural network. It is commonly used in applications where real-time processing is crucial. Now we will know what is YOLO V5N. It is a variant of YOLO designed for resource-constrained environments. It is a lightweight architecture to run on devices with limited computational power. YOLO V5N is used when there are constraints on computational resources, making it suitable for real-time applications on less powerful hardware. The next one is YOLO V5S, which is You Only Look Once version 5 small. YOLO V5S represents a smaller version of YOLO V5, often optimized for a balance between speed and accuracy. It is implemented for scenarios where a good compromise between speed and detection precision is required, such as in real-time detection applications. Coming to YOLO V7 Tiny, which is You Only Look Once version 7 Tiny. YOLO V7 Tiny is a compact version of YOLO V7 aimed at faster inference on the devices with limited resources. It is employed when the primary concern is on achieving real-time or near real-time detection on devices with low computational capabilities. The next algorithm is YOLO V5 GhostNet. YOLO V5 with GhostNet incorporates GhostNet, which is a lightweight backbone network designed for efficient and accurate feature extraction. It is utilized to enhance the efficiency of YOLO V5 by incorporating GhostNet, reducing model complexity, and potentially improving real-time performance. Coming to YOLO V5, YOLO V8N, which is You Only Look Once version 8 nano. YOLO V8 nano is applied when computational resources are limited providing a compromise between detection accuracy and speed. The next algorithm is YOLOv8s, which is You Only Look Once version 8 small. YOLOv8s represents a smaller variant of YOLOv8 optimized for scenarios where computational resources are moderate but speed is still crucial. It is implemented when a balance between model size, speed, detection accuracy is needed. As an extension, we applied other YOLO models to enhance the performance for detection and accurate final prediction. As an extension, we built the front end using Flash framework for user testing with the user authentication. We have used precision, recall, and map, which are the performance metrics to evaluate this project. So here we have performance comparison graphs for all these metrics. This is precision score comparison graph. Here on x-axis, we have precision score for each algorithm, and on y-axis, we have algorithm names. Similarly, we will have for other two graphs also. Coming to precision, it is a metric that measures the accuracy of positive predictions made by a model. It is calculated as the ratio of true positive predictions to the sum of true positives and false positives. Precision is concerned with the correctness of the positive predictions. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. Recall measures the ability of a model to correctly identify all relevant instances in a class. It is calculated as a ratio of true positive predictions to the sum of true positives and false negatives. This is MAP, which is mean average precision. Mean average precision is a metric commonly used to assess the performance of object detection models. It is calculated by averaging the average precision scores across multiple object classes. Average precision in turn measures the precision recall trade-off for a specific class by considering the precision at different recall levels. The algorithm which performs well among all these metrics will be used for final prediction. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. These are the two YOLOv5, YOLO7 folders in which we have datasets. We use those datasets for training the algorithms. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. This is the notebook file. This file is a Jupyter Notebook file which contains a combination of codes, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the sign up file. This file is the database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. By this, current directory will change to the code folder's path. Here we need to type the command python space app.py and then click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. This is the local host and this 5000 is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a sign up link first. We need to click on that and enter all the sign up details if we are signing up newly. I have already signed up and I have an account in it, so we'll directly click on login. Here we need to provide our credentials to login, so I'm giving my username and the password. And now we need to click on login. We have logged in successfully and we are redirected to detection page. Here we can see a choose file button. We need to click on that to upload the images. Based on the uploaded image, we will get the detection which type of disease the strawberry is affecting with. So I'm clicking on choose file button. From the folder, I'm selecting the first image, which is strawberry leaf. Now click on open. Here we can see that image has been loaded. Now we need to click on upload. Here we can see that application has detected the disease and it has drawn a bounding box around it, and it has classified the disease as angular leaf spot, and it has given a probability score for the disease detected. Probability score of detection represents the model's confidence level in accurately identifying an object in an image, with the higher score indicating greater certainty. Now we will upload other image. Click on back arrow. Click on choose file. This time I will upload the image. I'm uploading this image. Now we will click on open. Image has been loaded. Now click on upload. Here we can see that application has detected the disease and it has drawn bounding box around it, and it has classified the disease as anthracnose fruit. Now we will upload one more image. Click on back arrow. Click on choose file. This time I'll upload this image. Now click on open. And now click on upload. Here we can see that the application has detected the disease and it has drawn bounding box around it, and it has classified the disease as blossom blight with the 0.97 probability score. Now we will upload one more image. Click on back arrow. Click on choose file. This time I'll choose this image. Now click on open. And now we need to click on upload. Here we can see that application has detected the disease and it has drawn bounding box around it, and it has classified the disease as gray mold with 0.99 probability score. Now click on back arrow. Click on sign out. Similarly, if you upload the images to the system, then the system will detect which type of disease the strawberry is being affected with. Conclusion of the project. The project systematically explored and compared multiple YOLO variants including YOLO V5N, YOLO V5S, YOLO V7 Tiny, YOLO V5 GhostNet, YOLO V8N, and YOLO V8S through rigorous evaluation based on key metrics. The most effective model for detecting strawberry diseases in remote aerial satellite images was identified, ensuring optimal performance for the specific task. The implementation introduced the Ghost Conv module into the YOLO V5 network, optimizing model efficiency by reducing parameter numbers and floating point operations during feature extraction. This addition aimed at achieving a more resource-friendly approach, enhancing the model's computational efficiency without compromising accuracy. Model comparison was conducted based on a diverse set of evaluation metrics, including mean average precision recall. This thorough assessment ensured a balanced performance in terms of accuracy and efficiency, catering to real-time applications and deployment feasibility. The project integrated the Flash framework with SQLite, providing a secure sign-up and sign-in system. User authentication was implemented to ensure controlled access. The user-friendly interface allowed stakeholders, including farmers and researchers, to input images for the disease detection, viewed segmented objects, and interpret results easily, empowering them to actionable insights. The project aimed to deliver tangible benefits to stakeholders in the strawberry cultivation ecosystem by providing an improved lightweight YOLO V5 model for early detection of strawberry diseases.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.